have you ever wondered about the mysterious, unseen forces that shape our universe? Today, we delve into the realm of the extraordinary, the enigma of supermassive black holes. These cosmic giants, millions to billions of times larger than our sun, lurk in the heart of nearly every galaxy. Their gravitational pull is so strong, they swallow up everything that ventures too close. Even light itself, yes, you heard right. These monstrous entities are invisible to the naked eye, yet their influence is so profound, they shape the galaxies they inhabit. They're the ultimate puppet masters of the cosmos. But how do these cosmic giants form? How do they grow to such immense proportions? And how do they, despite being unseen, impact the structures of galaxies? These are the questions that have puzzled scientists for decades. Let's uncover the mystery of these cosmic giants, starting from their formation. So, how do these cosmic behemoths come into existence, you might be wondering? Well, the birth of supermassive black holes is a topic of intense study and debate among astrophysicists. Let's delve into the leading theories and try to unravel this mystery. One theory suggests that these giants are born from the remnants of the first stars. These first-generation stars, known as population 3 stars, were much larger and hotter than typical stars we see today. As these massive stars exhaust their nuclear fuel, they collapse under their own gravity, leading to spectacular supernova explosions. What's left behind is a black hole, a point in space where gravity is so strong that nothing, not even light, can escape. But these black holes are not supermassive yet. To grow into the behemoths we're talking about, they need to feed, and they do so through a process known as accretion. Accretion is basically the cosmic equivalent of an all-you-can-eat buffet. Black holes pull in nearby dust and gas, growing in mass as they consume more and more matter. Another theory posits that supermassive black holes could form from the direct collapse of enormous gas clouds in the early universe, bypassing the star phase altogether. This would allow for a much quicker route to supermassivity. Lastly, there's the idea of black hole mergers. Just as the name suggests, this theory proposes that black holes can merge to form larger ones. When galaxies collide, their central black holes can spiral towards each other, eventually merging to form a single supermassive black hole. It's likely that a combination of these processes contributes to the birth and growth of supermassive black holes. From their humble beginnings as the remnants of the first stars or as massive gas clouds, they grow, feed, and merge to become the awe-inspiring phenomena we're still trying to understand. From their humble beginnings, these giants grow to have a profound impact on their galactic neighborhoods. So, let's move on to explore the evidence of their existence, shall we? But how do we know supermassive black holes exist if we can't see them? A question that puzzles many, yet the answer lies not in what we can see, but in what we can observe. The heart of galaxies is where these cosmic beasts reside. Their presence may be cloaked in darkness, but their influence is far from subtle. The stars that orbit around the galactic center, they dance to the tune of the invisible maestro, the supermassive black hole. By observing these stellar orbits, astronomers have been able to measure the mass of the unseen entity, producing some of the most direct evidence for the existence of supermassive black holes. Yet this is not the only clue. Some galaxies, known as active galaxies, shine brighter at their centers than the combined light of all their stars. This extreme luminosity is too energetic to be explained by stars alone. The culprit? Active galactic nuclei, or AGN, powered by none other than supermassive black holes. As matter spirals into a black hole, it forms a hot, glowing accretion disk. This disk, heated to millions of degrees, outshines the entire galaxy. A beacon announcing the presence of a supermassive black hole. And then there are quasars, the most luminous and energetic objects in the universe. These celestial lighthouses, visible from billions of light years away, are thought to be powered by supermassive black holes, consuming matter at an extraordinary rate. Their immense energy output, often outshining entire galaxies, is a testament to the power of these cosmic giants. Each of these observations, from the ballet of stars at the galactic center to the blinding light of quasars, provides a piece of the puzzle. They allow us to peer into the darkness, to trace the silhouette of something we cannot see, to feel the gravitational pull of an entity cloaked in mystery. Despite their elusive nature, the evidence for supermassive black holes is compelling. In the grand cosmic detective story, the clues are scattered across the universe, waiting for us to piece them together. And the picture they paint is clear. Supermassive black holes exist, and their influence is profound. Just as the sun dominates the solar system, supermassive black holes rule their galaxies. These celestial behemoths aren't just passive spectators, they play an active role in shaping the galaxies they inhabit. Let's delve into the concept of coevolution, a theory that suggests galaxies and their central supermassive black holes grow in tandem. Picture a young galaxy bustling with gas and dust, the raw materials for stars. At its heart, a nascent supermassive black hole begins to feed, drawing in material with its extraordinary gravitational pull. As it grows, so too does the galaxy around it. This shared growth process is a cosmic dance, choreographed by the laws of physics. But the relationship between a galaxy and its central black hole isn't always harmonious. Sometimes the black hole's hunger outpaces the galaxy's ability to produce new stars. When this happens, the black hole can strip the galaxy of its gas and dust, stifling star formation. This process, known as feedback, can dramatically alter a galaxy's fate. Feed me and I shall thrive. Give me drink and I shall die. This old riddle captures the paradoxical nature of supermassive black holes. They thrive on the very material that can extinguish the life of the galaxies they inhabit. Yet it's not all doom and gloom. Feedback can also trigger starbirth. Here's how. When a supermassive black hole feeds, it can unleash a torrent of energy, sending shockwaves through the galaxy. These shockwaves can compress gas, triggering the birth of new stars. In this way, supermassive black holes can act as celestial midwives, aiding in the birth of the very stars they consume. There's another interesting aspect to consider. The mass of a supermassive black hole appears to be closely linked to the properties of its host galaxy, particularly the galaxy's central bulge. Bigger black holes reside in galaxies with larger, more massive bulges. This correlation, known as the M-sigma relation, hints at a deep connection between supermassive black holes and the galaxies they inhabit. In the grand cosmic scheme, supermassive black holes are not just destructive forces, but creative ones too. They not only shape their host galaxies, but also influence their evolution. They trigger starbirth, regulate star formation, and even sculpt the galaxy's central region. So the next time you gaze at the night sky, spare a thought for the supermassive black holes lurking in the hearts of those distant galaxies. They might be invisible to the naked eye, but their influence is written in the stars. With such immense power, supermassive black holes are the architects of their galaxies. What happens when two supermassive black holes get too close? It's a celestial tango unlike any other, a dance choreographed by gravity itself. When two supermassive black holes draw near, they don't just casually pass by each other. Instead, they engage in a gravitational ballet, spiraling ever closer until they eventually merge in a cataclysmic event that sends ripples through the very fabric of space-time. These ripples, known as gravitational waves, were predicted by Einstein's theory of general relativity over a century ago. But it wasn't until the 21st century that we developed the technology to detect them. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made history in 2016 when it detected gravitational waves from the merger of two stellar mass black holes. But supermassive black hole mergers? Those are on a whole different scale. We're talking about black holes that are millions or even billions of times the mass of our sun. When these titanic entities collide, they should produce gravitational waves that are proportionally more powerful. However, detecting these waves is a monumental task. They're low-frequency waves, much lower than the ones LIGO can detect. This is where the future space-based observatory LISA, the Laser Interferometer Space Antenna, comes into play. Designed to detect low-frequency gravitational waves, LISA might be our best bet to witness the dance of merging supermassive black holes. But why does this matter? What can we learn from these cosmic dances? Well, a lot, actually. Supermassive black hole mergers can help us understand the evolution of galaxies, as these mergers are often the result of galaxy collisions. They can also provide insights into the nature of gravity and confirm our understanding of general relativity. So, while we are yet to directly observe a supermassive black hole merger, the anticipation is mounting. The universe is a vast stage, and we, the audience, are eager to see the next act in this grand performance. These cosmic dances give us a glimpse into the dynamic nature of our universe. What is the ultimate fate of these cosmic giants? This question has intrigued scientists for decades. Supermassive black holes, those mysterious regions of space-time exhibiting gravitational acceleration so strong that nothing, no particles or even electromagnetic radiation such as light, can escape from it, have a fascinating life cycle. Let's take a moment to discuss one of the most intriguing theories about the eventual demise of these cosmic behemoths, a concept introduced by renowned physicist Stephen Hawking. Known as Hawking radiation, it suggests that black holes may not be so black after all. Instead, they might emit tiny particles, gradually losing mass over time. This process is incredibly slow, especially for supermassive black holes, but it could lead to their eventual evaporation. So how does this work? It all has to do with the peculiarities of quantum mechanics. In the vacuum of space, pairs of particles and antiparticles constantly pop into existence and annihilate each other almost immediately. But near the event horizon of a black hole, one particle might fall in while the other escapes. This escaping particle is what we call Hawking radiation. Now, while this idea sounds fascinating, there's a catch. The time it would take for a supermassive black hole to evaporate through Hawking radiation is unimaginably long. Far longer than the current age of the universe. So, even if this theory holds, these astronomical giants won't be disappearing anytime soon. But let's not forget, the universe is constantly evolving, and our understanding of these cosmic phenomena is still growing. As we continue to explore the depths of the cosmos, who knows what other secrets we might uncover about the fate of supermassive black holes? In the grand cosmic dance, these supermassive black holes play a critical role. And while their lifespan is beyond human comprehension, the theory of Hawking radiation suggests an intriguing possibility. Even these cosmic behemoths may not last forever. We've journeyed through the life and influence of supermassive black holes, but what are our key takeaways? We delved into their birth, exploring theories about their formation and growth. We examined the evidence of their existence, discovering the techniques used to detect these silent yet powerful entities. Their colossal impact on galaxies was laid bare, as we discussed the coevolution of galaxies and their central supermassive black holes and the feedback mechanisms they trigger. We witnessed the cosmic dance of black hole mergers and the resulting ripples they send across space-time. Lastly, we pondered the fate of these cosmic giants, introducing concepts such as Hawking radiation and black hole evaporation. These celestial enigmas, though shrouded in mystery, continue to captivate our curiosity and drive our quest for understanding. As we unravel the secrets of supermassive black holes, we uncover more threads in the intricate tapestry of our universe. Understanding these cosmic giants helps us unravel the intricate tapestry of our universe.